Okay, welcome everyone to my continuation of what is algebraic graph theory. Today I would like to talk about, well, whether the Tutte polynomial is actually easy or difficult in a complexity type of sense. So really it's about the complexity of the Tutte polynomial, but what I mean really is how to compute it, or how difficult is it to compute it. So the Tutte polynomial is very great, has a lot of graph theoretical information encoded, and can be computed algorithmically. That's not so bad already. But what I really would like to address today is more like, how reasonable is it to calculate it? Certainly for small graphs, that's totally fine. You can just list it, but maybe you can even compute it for kind of special families of graphs, like for all complete graphs or something. But what about the general? You take a random graph with a lot of vertices and a lot of edges. So how long will it take to compute the polynomial, right? In principle, there's an algorithm and you compute it, but in practice, so if you ask a machine, it just might take way too long. So let's talk a little bit about this complexity of the Tutte polynomial. So here's a reminder. So there's some kind of easy points like 1, 1, 2, 1, 1, 2 of the polynomial, and they count very interesting things like the number of forests, the number of spanning forests, subgraphs, something like that. So it's actually pretty cool, right? Remember that recall that the Tutte polynomial counts so many different things in one polynomial, which is pretty amazing, and that's why I called it easy. But kind of today's easy is a little bit different. I was rather interested in, as I said, how to compute it actually. So and by that I really mean not the algorithm itself, which I'm going to recall in a second, but rather the complexity of the computation of this polynomial. And as usual in this business, it's not really easy to write down the complexity of a problem. Most of the time you write down the complexity of an algorithm. So we'll see a little bit about that. Anyway, so as I just said, so our little polynomial friend here, the Tutte polynomial, counts so many great things. So we really would like to compute it somewhat efficiently. That I mean, well, as soon as your graph is big enough, you should really feed it into a machine. Don't do it by hand anymore for 1 million vertex graph. Well, at least I wouldn't do it by hand anymore. I probably wouldn't do it by hand anymore for a 3 vertex graph because I'm just super lazy. Anyway, and really bad in computation, by the way. But anyway, that's like, how fast can a computer do it? So certainly the algorithm itself is not a problem for a machine, but how fast can it do it, right? So how difficult is it to compute actually our friend, the polynomial? Or, which is not obvious why that should be the same, and in fact it's not, as we will see. And maybe we just, computing the polynomial itself is maybe very difficult and very hard, but what about computing values of the polynomial, right? So in this case, we evaluate it on some pair of complex numbers. That might be of the same complexity, or it could be easier, or it's not more difficult in some sense, unless the computation is really, really simple. So in this video, evaluating polynomials is usually, it's not free, it will cost a little bit, but compared to the computational time that you need to compute those things anyway, I can just kind of ignore it and kind of assume that evaluation of polynomials actually is free. I say it again, it's not, but everything else is so much more difficult that I can somehow assume that it is. Anyway, so here are two questions, and I like to stress the difference again: computing the polynomial itself, or computing certain evaluations of the polynomial. It's not clear why this should be of the same complexity type. Okay, before we can get going, I would like to recall for you, because I'm going to use it, the Landau-Bachmann notation. You might have seen that in the under the name capital O or big O notation. Kind of fun fact here. So originally this was supposed to be, this capital O that I'm writing here was supposed to be an omicron. So the Greek letter, you somehow can't distinguish omicron from O, and then it became capital O. But all the other ones, like this has an obvious symmetry. So for example, you can just flip it to flip the roles of f and g, or flip the positions of f and g rather. All the other complexity classes are called by Greek letters. So this is supposed to be an omicron. That was just a random fact. Don't worry about it too much. It's actually a very simple idea. And the picture summarizes everything, right? So that the function f is in a complex, is O of g if there exists a constant, which I forgot here in my little picture. So whether there exists a constant in front of g, and we don't care about the constant could be anything, such that from one point onward, f will be always lower than g. A little bit tricky here is that we are going to ignore this point here, and we're also going to ignore the constant. It's a little bit of a slightly weight notion. So it's not quite saying anything about some kind of complexity of a problem, because we're kind of ignoring those variables, but it kind of is a long run behavior. So for example, n is in O of n squared, right? So, and even 10,000 times n will be in O of n squared, because eventually, so for 10,000 times n, this n0 is very, very large, because it takes a while. That n squared will be faster than 10,000 times n, but the picture will look like this, and eventually my little function here will be smaller. And that's why it is in this complexity clause. And this is usually used to analyze worst case runtimes. So worst case runtime is very different from average case runtime. It's really kind of the hardest part, and we'll see that. So we're kind of ignoring the constant n0, we're ignoring the constant c, and we are only analyzing worst case scenarios. Why we do that is because then it's easier to make actual statements. Anyway, so that's the notation. So O of n is kind of the worst case, O of something will be the worst case runtime in this video. Okay, and as you can see here, this was our little recursion, the deletion and contraction, and you just do it. In each step, you have two choices, and eventually you get two very simple graphs, and every line gets associated to a polynomial in x, and every loop gets associated to a y, the variable y. So that's certainly an algorithmic way to compute the polynomial, but this looks quite difficult, because in every step, now imagine you have a big graph, so in every step you need to go two directions, right? So in every step you need to go two directions, 1, 2, so there should be some rows along 2 to the something. So this really probably looks like that in the worst case, like you can't, as you can see here, sometimes it goes all the way down, sometimes you could stop earlier, but in the worst case, where everything just is a binary tree, right, something like this, so it looks to me like, or it looks like this algorithm needs 2 to the number of edges computations, which is a lot. So 2 to the number of it, that's a really bad runtime. So it's exponential runtime. It's probably very difficult. That's kind of the point. It's not saying that the computation, and that's why I write properly here, of t itself is difficult, because this is just the runtime for one algorithm. There might be some smarter way of doing it, right? We don't know, and that's the whole problem in the field usually. But you can say something, and the result is quite nice. It's kind of a little bit surprising. So the computation, and now I'm really focusing on specific points. I don't know any result for the polynomial itself, but roughly it should be like this. Anyway, the computation for specific points depend on the points. It's kind of very strange. So in general, let's just do the general case. This is sharp p hard, which is really just saying it's really, really difficult. So it's something like exponential growth. Let's not worry about it. So the general situation, just random evaluation of numbers, is really, really difficult. Okay, so sharp p hard, whatever that is, it's a certain complexity class. And as I said, it's roughly like exponential growth. But for values on this hyperbola here, this little hyperbola, or the real picture of the complex hyperbola given by this equation, for example, 2 and 2 is here, or whatever, this point, or whatever, all the points here. So 2 and 2, a equals 2, b equals 2 is, for example, on this hyperbola. And for them, it's actually, evaluation is like tremendously much faster. It's a polynomial. So something like n cubed plus n. I haven't found a good reference what it is precisely, but it will be something like whatever, n cubed plus n squared, and maybe 10 times, something like that. Some polynomial, right? So some polynomial in the number of vertices. So everything here, sorry, in the number of edges. And then there are some points, some isolated points, 8 of them, 1, 1, -1, 0, -1, whatever. And those is also easy. Okay, so here, for example, our little point at 1, 1, the number of spanning forests is actually easy to compute. It's kind of fun. So the number of spanning forests is one of these exceptional points, and otherwise there's this hyperbola where it's easy, and in general, it's just forget it. It's just really, really difficult. And I really would like to stress, I like this a lot, this huge difference between kind of the general calculation and evaluation at specific points, right? Along this hyperbola, which I will call h in a second, it's kind of really simple, and I will just, strictly speaking, I will call this h1, and I will call h the union of h1 with this little set here, and I just call it still a hyperbola. But anyway, so along this hyperbola, it's kind of easy, and otherwise it's kind of hopeless. It's kind of a fun fact. So it kind of tells you that the information in the Tutte polynomial kind of splits into different things. Some points are hard to get, so whatever you count is a difficult problem in some sense, and some other points are easy to get, so whatever you count, it's an easy problem. I still think most problems here encoded are easy because somehow you can encode everything at once, but from the complexity class, there's really a huge difference between the ones you can easily get and the ones that are hard to get, right? So that's kind of very different. And here is kind of the summary of what I know is true. Kind of ignore this complexity clause. So this is essentially exponential, this is sub-exponential, and this is polynomial. So for all graphs, it's exponential essentially everywhere, except on our hyperplane. And our hyperplane, it will be actually polynomial and therefore also sub-exponential. But then you can play around, right? We're doing the worst case scenario. There might be some graphs where it's actually much better. So, for example, if the click width, the size of the largest click is not too big, it's somehow bounded by some number, then actually everything is already sub-exponential, right? On this class, it's somehow much easier. And ignore the others. So for planar, it also looks a little bit like for all graphs, but your hyperbola changes. And similarly for bipartite planar, your hyperbola changes. And for those classes here, whatever they are, certain classes of graphs, it's just much easier. It's in general already sub-exponential, right? So computing this polynomial is difficult in general, but it doesn't mean that computing it on certain special classes is difficult. And this is exactly what it happens here. So if you have a certain graph and it falls in this little class here, then computing it is actually not so bad at all. Right, so that's what I was trying to say. Okay, so kind of the idea of this video was to give a little kind of little tour through complexity theory, not really, right? So I was just explaining complexity of the Tutte polynomial, but I think it's a cool blueprint example because just saying the general computation is difficult, and in this case it is, doesn't say that it's difficult all the time. And that's exactly what we have seen. So that's, for example, this hyperbola, where somehow it's much, much easier, like polynomial compared to exponential. But in general, it's just very, very difficult. Anyway, I hope you enjoyed this video, and I also hope to see you next time.